Exercise set 1.4. Applications. Two-variable linear systems of equations. Standards of solutions. Define all variables. Explain the source of any newly introduced equation. Assess the correctness of the solution by performing two types of checks: a check of the math problem solution and a check for sensibility in the real world. Of the two checks, the latter is the more important. Be reminded that the most likely source of error in an application problem lies in the translation from the real-world problem to the math model problem. Thus, the importance of a sensibility check. Calculator usage is required. Exercise 5. It took a patrol boat 5 hours, 23 minutes to travel 75.4 miles up a river against the current, and 3 hours, 37 minutes for the return trip with the current. Find the speed of the boat in still water and the speed of the current. In each case, round to 3 significant digits. Alright, let's see. For variables here, well, you probably might do well to go with something such as letting x equal the speed of the boat in still water. In this case, let's also note the units of measure we have in mind for x here. Now, you can decide a variety of things here, but once you decide, you need to stay with it throughout your math model. In this case, since the distances are in miles and the times are, well, hours and minutes, let's go with miles per hour for our speed of the boat, units of measure. So in parentheses, mph, common notation for miles per hour. And then we can similarly go with y to be the speed of the current. Okay, and that'll be miles per hour. Okay, now what can we do about getting some equations formulated here? Takes this patrol boat 5 hours, 23 minutes to travel 75.4 miles up a river. Okay, looks like this would be a chance to use a physical principle here, and that's that we can say that, okay, distance equals speed times time. As long as speed is constant, you can use this simple algebraic expression here, formulation here. Alright, in our case here, we do have, at least when the boat is going up the river, the speed is constant, so we can make use of this. Now, let's see here. The distance in this travel is 75.4 miles. The speed, now when the boat is traveling up against the current, the speed would be the still water speed minus the water speed. Water's working against the boat now, slowing it down, so we need to account for that in our formulation of speed. And then the time, okay, 5 hours, 23 minutes. Alright, since we have decided to stick with miles here and hours, we need to write this in terms of hours only, and so we'll need to say 5. What about 23 minutes? Okay, plus 23 over 60. Alright, this would become equation 1. Okay. Now, let's see, what else can we do for information? Once again, we can now consider the same idea. This distance equals speed times time is important to us. let's see, to maybe help organize our explanation, this is the upriver situation and leading us to equation 1. Now let's consider down the river with the current. Okay, what do we have here? Well, the return trip has the same distance. Now as far as speed, well, when traveling with the current, you would have the still water speed of the boat plus the water current adding together to give you your speed there. And the time in this downriver situation, 3 hours 37 minutes, okay, written as hours, would have to be 3 plus 37 over 60. There could be equation 2. Okay, at this point, it appears we've used all of the information in the problem. It's all accounted for in our math model. What kind of math model have we got here? All right, notice this equation is linear in x and y. This equation also linear in x and y. And together they constitute a system. So we could say, although you don't have to write this, but be in the habit of noticing what kind of math problem have you got here. In this case, observe that equations 1 and 2 constitute a linear system. Of equations. 2 variable. Okay. Well, we're pretty good at these. Let's see. Let's plan for maybe a calculator solution here. Now, let's see. Yes, we want to solve for y in each case here. Starting with equation 1, let's see. We could divide both sides by this 5 plus 23 divided by 60. And then we could subtract an x from both sides and then multiply both sides by negative 1. We would have y1 equaling 2 x minus 75.4 over 5 plus 23 over 60. Okay. For the second equation, if we go to solve for y in this case, divide both sides by 3 plus 37 over 60, then subtract x from both sides. Okay, y sub 2 is equal to 75.4 over 3 plus 37 over 60 minus x. Alright, looks like we are ready to go to the calculator. Okay, let's go to the y equals 2 edit screen. And in the case of y1, we have here x minus 75.4 divided by parenthesis 5 plus 23 divided by 60 and then another parenthesis. In y2 we've got 75.4 divided by parenthesis 3 plus 37 divided by 60 parenthesis minus x. Alright, now let's see. As far as a coordinate system, let's think about this window here. Now x, looking back at our definition, it's the speed of the boat in still water. Okay, it's a patrol boat. So just what kind of numbers are even sensible here? Oh, let's maybe say 0 to 60 miles per hour. At 60 miles per hour, we're getting into a racing boat territory, not patrol boats any longer. So maybe we start with that as our consideration. Off to the window. Looking at 0 for X-Men. And let's just guess 60 for an X-Max to be looking at everything that's reasonable. And then let's have the calculator concern itself with getting the graph to appear by having it go zoom fit. Okay, looks like we have a single point solution in this problem. Let's go get it. Second, calculate, intersect. That's our y1. That's our second curve, our y2. And as far as a guess goes, let's move the graph cursor over to about there. Enter. Alright, let's take these numbers and get ready and start to write our conclusion about all this. Okay, looking at those calculated numbers, we have our x sitting there. The question requested us rounding to 3 significant digits. Let's review our definition of x. What was that again? Okay, this is the speed of the boat in still water, miles per hour. So let's record the speed of the boat in still water is 17.4 miles per hour. The y, in our case here, rounding to 3 significant digits, becomes 3.42, and the units of measure, miles per hour, and this is the water current speed. The water current speed is 3.42 miles per hour. Alright, so our major conclusion of this question. Now, let's go ahead and check this over. Okay, first, just the math problem check. How about that? Well, let's see. What could have gone wrong? Maybe there was a mistake in the solve for y's before we went to the calculator. Or maybe we did some keystroke errors. Okay, so let's review the original equations. Substitute into original equations. Okay, the left hand, let me take the right hand side of the equation 1. That's the x minus y times 5 plus 23 over 60. Get a number from the calculator there. The second original equation, let's take its right hand side, x plus y, and then 3 plus 37 over 60. Let's see what happens there. Okay, let's go. Okay, at the calculator, we can take this first equation's right-hand side. That is, parenthesis, x minus alpha y, parenthesis, times parenthesis 5 plus 23 divided by 60, parenthesis, go. Okay, 75.4. That's the number we need to make the first equation true. Alright, let's try the second equation, the right-hand side, parenthesis x plus y, parenthesis, 3 plus 37 divided by 60, parenthesis, go. Okay, that looks good. That takes care of our math check, at least, is in order. Let's go back to the paper. Okay, so here the calculator came up with a 75.4. That matches our first original equation. Check. In the second situation, it came up also with 75.4. That meets the left-hand side of the original equation. Looks good. There. Now, what about sensibility? Okay. So there's the math check. Sensibility. Maybe here we could just kind of examine the kinds of numbers we got here and see if these are consistent with real world boats and currents. For instance, this patrol boat speed. Patrol boat speed of 17.4 miles per hour is reasonable. What do we think of a patrol boat? If you watch one in the rivers or the oceans, 17.4 miles per hour, that's like a good bicycling speed. Okay, so this is pretty fair for a patrol boat to be going at this kind of pace here. No problems there. Secondly, what about the water current? What do we have there? The water current speed of 3.42. Okay, if you take a look, you can go online, check out the speeds, current speeds of rivers throughout the world. Check the Amazon, the Nile, the Ganges, all these rivers, and basically they're all between like 1 to 7 miles per hour for the most part. So we could say here this water current speed of 3.42 miles per hour is within the common range of river current speeds worldwide. Alright, what we're looking for are answers that are really kind of crazy. Like if we find a patrol boat 174 miles per hour, now we start to think, wait a minute, that's not any normal patrol boat. This is starting to feel nonsensical. Or the same thing if the water current for some reason came out to be 342 miles per hour. Again, we should be thinking, wait, that's not sensible with physical reality, and then we should reject our solution based on that in that case as well. But here, both these numbers are pretty much consistent with what we see in our everyday lives with patrol boats and river currents. So we like this answer. Let's go a little further with this check of this patrol boat speed of 17.4 miles per hour. Let's try to challenge this number here with a very, you want to try to challenge your answers with very simple calculations. Make sure everything is consistent. So here, let's do this. The time it would take the patrol boat to travel 75.4 miles in still water would equal, let's see, we have the distance equals speed times time, so time equals distance divided by speed. That would mean 75.4 divided by the 17.4 we have here. And this is about equal to, okay, get a little calculator, 75.4 divided by 17.4. Okay, about 4.333. Now let's see, how would that be in terms of hours and minutes? We could subtract the 4 hours, and although it's not a surprise here, I don't suppose, we could now multiply this by 60 minutes per hour. So we're looking at 4 hours and 20 minutes. Okay. Here, 4 hours, 20 minutes. Now, what do we expect of this time in still water? Well, we expect it to be intermediate between the time that it takes the boat to do this with the current and the time it takes the boat to do this without the current. Is that the case? Well, the against the current time was 5 hours 23 minutes. The with the current time was 3 hours 37 minutes. Okay, so we continue the good news here, which is intermediate to the times required for against current and with current. This is the expected result. Okay, so now that 17.4 miles per hour is really looking pretty good. Okay. Exercise 7. Vinegar is a solution of acetic acid in water. At a grocery store, it is available as a 5.0% solution. At a garden supply store, it is available as a 10% solution. Vinegar, by the way, is amazingly useful. You can ingest it as part of your salad dressing, perhaps, or you can turn around and use it as something to kill microorganisms. It just does all kinds of things. Anyway, how many milliliters of each type should be mixed to produce 75 mLs of 6.2% acetic acid? Okay, let's decide about defining our variables. A lot of times, what you're asked for has a lot of control over how you define your variables. In this case, since we're seeking how many mLs of each type, this might lead us to these kind of definitions. Let x equal we'll use the word volume of 5% acetic acid to use, and then we can claim y, or define y, to be the ditto marks volume of 10% acetic acid to use. And let's see here, we should include the units of measure we plan to be going with here. mLs looks good in each case there. Alright, let's see, what have we got for source of equations here? Alright, this item here, we are producing 75 mLs of this 6.2% acetic acid. Okay, so we can say that our total volume is 75 mLs. That would lead us to an equation which is volume of 5% acetic acid plus volume of 10% acetic acid. It's got to equal 75. Okay, there's equation 1. Got an equation. Alright, now what? Sometimes you can use a conservation principle as a source of equation, and it's surprising how powerful conservation principle can be it conservation of energy, conservation of mass, conservation of momentum. If you're a scientist or an engineer, there's just no end of conservation principles that get used to create equations. In this case here, we can use it to conserve the acetic acid itself. Now, since there are no chemical reactions in this process, we're just mixing things, we can go with conservation. So we can talk about conservation of acetic acid. And let's elaborate on that. So what do we exactly mean by conservation of acetic acid? We mean that the volume of acetic acid from the components, that is, the two items that are being put into the mix, has got to equal the volume of acetic acid in the final solution. Okay, I think from this we can now translate into some math. Now, the volume of acetic acid from the components. There are two components here, a 5% solution and a 10% solution. Alright, how much acetic acid comes from that 5% solution? You would need the total volume times 5%. In our case, we've used x to represent that volume, so 0.05x is the amount of that first item, which is acetic acid. Add to it, okay, how much acetic acid comes from the 10% solution we add? Well, the percent acetic acid, 0.10, times the volume of it, which is the y. A volume of the vinegar, that is what we mean here. Okay, so this tells us the acetic acid coming from the 5% solution. Here's the acetic acid coming out of the second solution. And this has to equal, now, how much acetic acid is in our final mixture? The final mixture is 75 mLs of 6.2% acetic acid. So the volume of acetic acid amongst that would be 0.062, 6.2% times 75.0. Percent times volume. Okay, and this has given us equation 2. Let's see. Sometimes you might decide to do a little touch-up of your original equations. This has a fair number of decimals which could be pretty easily eliminated. Maybe we multiply both sides of this by 100 and have it look like 5x plus 10y equaling, let's choose to multiply the 100 by this number here, and that makes that 6.2 times 75. You could, if you wanted to, even divide both sides by 5. If you want to keep kind of making this look a little nicer, 5 divides both sides evenly. X plus 2y equals 6.2. Now this divides by 5, leaving us with 15. Okay, and we could call this equation 2a. when I'm organizing my solutions, the fundamental equation gets the fundamental number, and then if it's something that's derived from it, it gets A, B, C, D thereafter. Okay. Anyway, what kind of math problem have we got here now? Well, the equation 1 and equation 2, A, constitute a linear system. Okay. Observe. Equation 1 and 2A constitute a linear system of equations. In two variables. Okay, let's go ahead and solve them. Let's see. If we were going to use the calculator here, we could take the first equation, solve for y. Y equals to 75 minus x becomes a y sub 1. The second equation, we would have subtract x from both sides, divide by sides by 2. Y sub 2 could equal 6.2 times 15 minus x divided by 2. Okay, let's go to the calculator. Okay, at the calculator, go to the y equals to edit screen. Let's put in our y1, 75 minus x. For y2, we have got parenthesis 6.2 times 15 minus x parenthesis divided by 2. Alright, now a coordinate system. Let's make sure we have everything sensible for x in sight. In other words, we'll go to the window. Okay, so we can have the x go from 0 to 75. And then we can have the calculator control the y-axis so that the graphs are in sight. By that, we'll do a zoom fit. Okay, looks like a single point solution. Let's go get it. Second, calculate, intersect. That's our y1, first curve. That's indeed our y2, second curve. For a guess, let's move that calculator cursor to be about at the intersection, about there. Okay, let's go ahead and record this as a conclusion, interpreting it at the same time. Alright, so looking at our calculator display here, x represents, again looking back at our definition, the volume of 5% acetic acid to use. So we can start to make a sentence. Should use 57 mLs of 5% acetic acid and 18 mLs of 10% acetic acid. This is our major conclusion. Now, let's start to check this over a bit here. The instructions of this exercise set are looking for two checks. One, a math check. And secondly, and more importantly, a sensibility. Okay, first the math. What about that? Well, here's where we could go to the original equations and make sure that when we substitute these numbers in, it makes each of them true. So our math check will be a matter of substitute into the original equations. Okay, I'm going to equation 1. Its left-hand side is x plus y equals. Work that out on the calculator. And the second original equation, now I'm going to use the actual original equation 2, not even the 2a, because maybe some mistakes were made along the way of getting that derived equation. Okay, now on the first equation, the left-hand side is 0.05 x plus 0.10 y, and in this case its right-hand side is not computed as a single number, so we'll have to also do that. So in other words, this here is the left-hand side, LHS. And over here, we'll also compute the right-hand side, which was the 0.062 times the 75.0, and see what that is. Okay, time to return to the calculator for a moment. Okay, on the home screen of the calculator, let's try this first equation's left-hand side, and that's the x plus alpha y, enter. Okay, 75, sure. Now, the second equation, 0.05x plus 0.10 alpha y. Okay, get that. Now the right-hand side of that equation, that was the 0.062 times 75. Enter. Okay, good. Looks like at least the math part of this is in order. Let's go back to our paper, record our results. Alright, so we've got this to be 75, which is just as equation 1, right-hand side. Now, the second equation, this came out on the calculator to be 4.65, and the right-hand side came out to be the same, 4.65. Okay, so these two now equal, so that's in order. Now, how about sensibility? Okay, what to do here? Well, let's see. We could consider this solution here and notice that it's supposed to be 6.2% acetic acid, and the components are a 5% and a 10%. So think about that. 6.2% is quite a bit closer to 5% than 10%. So we would expect this solution to be dominated by the 5% solution. And if we look at our answer, that's indeed the case. Alright, so let's record that. The end mixture, the final solution, is to be 6.2% acetic acid which resembles 5% acetic acid more than 10% acetic acetic acid. Thus, we expect the majority of the mixture to be 5% acetic acid. And looking at our numbers there, 57 mLs is 5%, only 18 mLs is 10%. This is indeed the case. Okay, so now these numbers here start to feel even intuitively correct, as well as fitting the math model. Okay, looks good.